On a Riemannian manifold, the Laplacian is the operator negative div of grad. This can also be expressed as minus star d, where star denotes Hodge star with respect to the metric. This is a differential operator on smooth functions and vanishes precisely on the harmonic functions. In geodesic normal coordinates at a point x, the Laplacian of phi is equal to the negative of the sum of the second partial derivatives of phi with respect to the coordinates. A coordinate-free way of expressing this is to say that the value of the Laplacian of phi at x is minus n times the average of the second derivative of phi on a unit speed geodesic through x. On a surface, changing the metric conformally by some factor changes the Laplacian by multiplication by the inverse of that factor. So the property of being a harmonic function on a surface is conformally invariant. This makes sense because the harmonic functions are exactly the real part of the holomorphic functions. The Laplacian is closely related to the notion of Brownian motion on a Riemannian manifold. Brownian motion is a probability measure on paths on the manifold. It may be obtained as a scaled limit of random walk. Fix a step size 1 over n, and then take Tn squared random steps of size 1 over n. This gives a probability measure on paths starting at an initial point for each n. If we take the limit as n goes to infinity, this law on paths converges to Brownian motion. Notice that it is possible for a random walk consisting of n squared steps of size 1 over n to move a distance up to n from the origin. However, the central limit theorem says that n squared random steps of a fixed size are likely to move only order n times the step size away from the origin, and therefore, in the limit, Brownian motion is a law on continuous paths. For a point x and a time t, let ktx be the probability measure on our manifold M, whose value on a set U is the probability that Brownian motion for time t starting at x ends in the set U. This probability measure is absolutely continuous with respect to the volume measure, at least when t is positive. So we may write it as ktxy dvol, where ktxy is a smooth function on M known as the heat kernel. It is symmetric in x and y and solves the heat equation. dk dt is the Laplacian of k. And furthermore, as t converges to 0, ktxy converges to the Dirac function at the point x in the sense of distribution. Convolution with the heat kernel defines an operator called the diffusion operator. For each time t, convolution with ktxy defines the diffusion operator capital DT. Thus, the value of the diffusion operator on a function f at a point x is equal to the expected value of f of y, where y is the result of a time t Brownian motion starting at the point x. Now let's discuss laminations. Let lambda be a lamination, whose leaves are Riemannian manifolds. A probability measure mu on lambda is said to be harmonic if the expected value of the Laplacian of f with respect to the probability measure mu is 0 for all leafwise smooth functions f, where the Laplacian is the leafwise Laplacian. The fundamental theorem of Garnett is that every compact Riemannian lamination admits a harmonic measure. Let's prove this. First, we give the idea of a proof. Let's let dt denote the leafwise diffusion operator. This means, for each leaf, dt of f is convolution with the heat kernel. Let's assume for now that dt is continuous. The action of the diffusion operator on functions gives rise to an action on measures, where the integral of f with respect to dt of a measure nu is defined to be the integral of dt of f with respect to nu. Since dt of f is convolution with the heat kernel, the time derivative of dt of f is equal to the Laplacian of f. So a measure mu is harmonic if and only if it is invariant under the leafwise diffusion operators. Using this fact, we can construct a harmonic measure as follows. First, choose any probability measure nu. Then define nu sub n to be the average of the leafwise diffusion operator of nu for times 1 through n. This defines a sequence of probability measures nu sub n, which converge to a limit mu, which by construction is invariant under the leafwise diffusion operator and is therefore harmonic. The theorem is proved providing that we can show that the leafwise diffusion operator dt is continuous. This is actually rather subtle. Remember, dt of f at a point x is equal to the expected value of f under time t leafwise Brownian motion starting at the point x. Since leafwise Brownian motion and diffusion behave well under taking covers, without loss of generality, we can work in the universal cover. Let's consider 2 points, x and y, contained in leaves lambda and lambda prime, and let's suppose x and y are very close. Therefore, the leaves lambda and lambda prime are very close on some big balls centered at x and y. Since the leaves are close throughout this big, although finite region, the values of the function f are very close. However, outside this finite region, there is essentially no relation between the leaves lambda and lambda prime, and the values of f are essentially uncorrelated outside this region. In order to show that dtf of x is close to dtf of y, we somehow need to control the contributions to dtf of x and of y from the geometry of the leaves outside these big balls. The problem is, Brownian motion for any finite time has a positive probability to move any distance from its initial point, and therefore dt of f has contributions from the values of f on the entire leaf. Let's look at this in a little more detail. Time 1 Brownian motion is the limit of a sequence of random walks, the limit of n squared random steps of length 1 over n as n goes to infinity. So there is a positive chance random walk for time 1 can travel any distance r from its starting point, and the same is true for Brownian motion. However, this probability falls off very quickly with the distance r. A Riemannian manifold is approximately Euclidean on very small scales. In Euclidean space, the Chernoff inequality, or really the central limit theorem, says the probability that a random walk of length n squared travels a distance greater than or equal to Rn times the step size from the origin falls off like a Gaussian, e to the minus some constant times r squared. Taking limits, this implies that Brownian motion on lambda for time t stays inside a ball of radius r with probability 1 minus e to the minus constant r squared. We may therefore estimate the difference between dtf at x and dtf at y by splitting it into two terms, one coming from those Brownian motions which stay in the parts of the leaves that are very close. This will be a small number because the values of f are very close there, plus a term which counts the contributions from Brownian motions that move outside this ball. This term is bounded by the sup norm of f times e to the minus constant r squared, which is very small when r is big. Therefore, the leafwise diffusion is continuous, and the theorem is proved. Now let's discuss disintegration of harmonic measures. Let mu be a harmonic measure on lambda. Let's look at mu in some product chart u equal to r to the n times x for some local leaf space x. The measure mu restricted to u pushes forward by projection to a measure nu on the leaf space x. And there are a family of leafwise Borel measures mu sub x on the leaves Rn times x, so that the integral over u of f d mu is equal to the integral over x of the leafwise integrals f d mu x over the leaf Rn times x. By uniqueness of disintegration and dt invariance of harmonic measures, it follows that each leafwise measure mu sub x is of the form hx d vol, where hx is a non-negative harmonic leafwise function. As we move from chart to chart, this decomposition can change so that the functions h sub x on the leaves are defined only up to multiplication by a constant. If lambda is a leaf in the support of the harmonic measure mu, and lambda twiddle is its universal cover, then we can choose a global lift h twiddle, which is a non-negative leafwise harmonic function on lambda twiddle. Now let's suppose lambda is a Riemann surface lamination. Only a conformally hyperbolic leaf admits a non-constant positive harmonic function on its universal cover. It follows that every parabolic leaf in the support of a harmonic measure mu, this function h sub x is actually a constant. After scaling this constant leafwise to be equal to 1, we obtain a family of local measures nu sub x on the local leaf spaces, which piece together to define an invariant transverse measure.